Okay, in our previous segment, we talked about how to calculate your weight. Now we want to talk about how to calculate the force of friction. So, what do we mean by the force of friction? So, if you take a box and you give it a shove, you apply a force to it. And so then, as soon as you stop applying that force, according to Newton's first law of motion, that box should move with a constant speed. But normally it doesn't. So that box comes to a stop. So the reason why it comes to a stop is there's another force acting on it. So an object stays in motion at a constant speed unless another force acts on it. And then that will change its speed. So the box comes to a stop because there's another force acting on it, and that's going to be the force of friction. The force of friction always opposes motion. So that if you've got a box and it's trying to go in this direction, then the force of friction will be this way. It will be in the opposite direction. If you've got a box and that box is trying to go this way, then the force of friction is going to be that way. So it always opposes motion, and it will always slow down the motion of the object. So what does the force of friction depend on? Okay, so we can do some very simple experiments to verify this. So imagine that you've got two boxes, and these two boxes are resting on, let's say, linoleum, plastic, but this one has a mass M, and then this one has bricks in it. So this one has a much larger mass. Now you're going to give them both the same shove. Which one comes to a stop first? Okay, I think you can visualize this in your head. You could try the experiment and you would find out that this one would come to a stop first. So that the force of friction depends on mass. Now we could even say, let's write it over here, the force of friction, and I'll give you two possibilities. So is it proportional to M, or is it proportional to 1 over M? So which one makes more sense? So you just got through saying, I hope you said, that this one here, the one that has the most amount of mass, comes to a stop first because it's experiencing more friction. Well, that's this case here. So this one would imply the larger the mass, the smaller the friction, and it would travel further, but it doesn't. So that means that the force of friction should depend on the mass of the object. Case number 2. All right, case number 2 is that we've got two boxes and they both have the same mass this time. But the difference is this one's going to be on ice, and then this one is going to be on rock. So this one's sliding on rock, and then this one like gravel, and then this one's sliding on ice. Which one's going to go further? I said further, and that's going to be the ice, okay, because this is smoother. So the smoothness of the two surfaces is going to be called the coefficient of friction. And so that is going to be given by this symbol here. It's called mu. It's kind of like what a cat does. So mu is this symbol. It's the coefficient of friction, and it depends on the two surfaces. So this was, let's say, cardboard, and then this was ice. This was cardboard, and then this was gravel. All right, so different substances have different coefficients of friction. And in just a moment, I'm going to show you some different coefficients of friction. All right, can you imagine what case number 3 is going to be? We'll have the same boxes. They're going to rub against the same materials, but we're going to do it on Earth, and then we're going to do it on the moon. Okay, so which box? The box on Earth or the box on the moon? Which one's going to slide further? It's going to be the moon, because the moon has less gravity. So that's the third variable, which is going to be the letter G, gravity. Actually, the acceleration due to gravity, that 9.8 thing. So that's what that thing is, 9.8 meters per second squared. So it depends on what planet that you're on. Well, we're going to be on Earth when we do our tests. So most of the questions, if it has to do with friction, you can assume it's happening on Earth. So we're not going to be changing the G thing. But if you went to the moon, G would be 2. If you go to Earth, G is 9.8. So these are the 3 things that the force of friction is going to depend on. All right, so here is, again, a conceptual question. Which is harder to move, a light box or a heavy one? And so here's our equation. Shows that friction depends on mass. So a heavier box causes more friction and is going to be heavy or harder to move. Now we could also do a math problem. So we could, if you knew what the mass was, so let's say, just for the sake of argument, that the mass is equal to, I'm running out of room here, so have a cup of coffee. Just wait a second. Get rid of all of this. All right, so there we go. So let's say that the mass is 2 kilograms. Let's say that the coefficient of friction, and I'm going to show you coefficients of friction in just a moment, but let's just say, for the sake of argument, it's 0.3. And then we know that G is equal to 9.8. So we could multiply these 3 numbers together, and then we would have the force of friction in newtons. So we could actually calculate how strong this force of friction would be, but we're not going to do it. So we're just going to stick to conceptual questions with this. So here are some typical coefficients of friction. So rubber on dry concrete. So think about your car, your rubber tires rolling on concrete. It has a coefficient of friction of 1. But look at what happens on a rainy day. Rubber on wet concrete is 0.7. So on a rainy day, you lose 30% of your traction. So that's the reason why you got to be very careful when you are driving on snow and on ice, because you lose traction, and therefore the force of friction between your tires and the road diminishes. And then way down there at the bottom, you see synovial joints. So in all of your joints, you have these little pads that connect the 2 bones. And then inside those pads are these this very slippery material, and it's called synovial fluid. And you can see that it has a very, very small coefficient of friction. And so that keeps the 2 bones from rubbing up against each other. Okay, so let's take a break. When we come back, what's the point? So why are we interested in Newton's second law of motion? So I'll see you in just a moment.